Welcome back to the course in Nuclear Medicine Physics. Today, we're continuing our discussion on radiopharmaceutical therapy, or more specifically, internal dosimetry. Now, if you inject a patient with a radiopharmaceutical that binds to a tumor, or goes to a certain region of the body, for example, while the radiation is emitted in that region of the body, it's not going to be absorbed only in that region of the body. For example, if that radiation goes to the liver, radiation will be emitted that it gets absorbed everywhere, for example, in the stomach, in the lungs, in the heart, and all the different organs of the body. The purpose of internal dosimetry is to say, if I have a certain amount of radiation in one region of the body, how much radiation do the other organs of the body receive? We'll start by looking at some basic mathematical formulas that allow you to get an estimate of such things. In practice, however, this differs from patient to patient because everybody has a slightly different body composition. This is just one of the challenges of internal dosimetry, and we'll look at some others as well.
But the way it works is, okay, we're gonna think that we're gonna have source organs and target organs. So for example, in this case, maybe the liver I'm gonna count as the source organ, and maybe the target is gonna be the kidney. It can also be reversed, but what we're gonna think is, okay, we're gonna have we injected the patient, some of the radioactivity went to the liver. Now, there are some emissions coming out of that liver that might end up making it to the kidney. So we want to see, if we know everything that's happening in the liver, if we know all the amount of radioactivity in the liver, can I try to measure from all those emissions how much energy is deposited in the kidney? Now, the source and the target can be the same. So I can ask the question, okay, if I have this radioactivity in the liver, how much energy is that activity depositing in the liver? So source and target can be the same. Or I can ask, maybe now I can also look at the kidney being the source, and I'm asking the question, okay, if I have this radioactivity in the kidney, how much energy is deposited in the liver? So this is just to show that we're basically going to have to do some permutations between all the different organs all around the body. Okay, but to calculate those in nuclear medicine procedures, well, we need to have information from the radioactive emissions of the radiopharmaceutical. And I think we mostly know that very well. Earlier in the course, we talked about radioactive decay. We saw the NUDAT website that provides information of the decay for many, many different radioisotopes. We can see what type of particles are coming from that decay, what's the energy of that decay of that particle, what's the probability that I get particle A compared to particle B, and so on and so on. So let's think again. Let's look at when we have the source and where we have the target. So if I want to calculate the energy deposited in the target, I need to know, okay, let's look at one particle. Let's look at one decay. So one decay might produce a particle with some energy. Okay, so that we have a particle of that energy traveling towards the kidney. Now, that particle might have some interactions in the kidney, but maybe it doesn't necessarily have to deposit all the energy in the kidney. So for example, you have a photon, it's coming to the kidney, it interacts through Compton scattering in the kidney. So it deposited some of its energy in the kidney, but the scattered photon leaves the kidney. So that's what this finding. So we're looking at, okay, what's the probability that I get a particle of energy I from that decay, and then this phi is giving us what is the fraction of total of this energy that gets absorbed in the kidney. And we're going to do that for all the possible particles coming out of one decay. So this basically, the numerator is basically telling us the total energy that was deposited in that target. If I divide that by the mass of the target, then this is joules per kilogram. But remember, we did this for one decay. Okay, and we call this the S factor. We group this in what we call the S factor, and this notation represents, this is the S factor basically from dose from a particle that comes from a source and deposits its energy in the target. So from source to target, that's what that means. So the S factor is providing us information about the dose absorbed by that target per decay in the source. Okay, so basically, again, this is the dose from one decay. So you can think, okay, if I want to calculate the total dose, and I know the dose in one decay, well, then it should just be as simple as saying, okay, let's calculate the total number of decays times the dose per one decay, we get the total dose. So how many decays do we have in total within the source? Well, maybe that should be very easy, because earlier in the course, we talked about activity, and we said that activity was number of particles decaying per unit time, and it followed a relationship like this. So if I want to find the total number of particles, the total number of decays, then I'm just going to integrate that, and that integral is going to be easy. So basically, I solved the problem. And well, yeah, mostly, but we have to keep in mind that there are some more biological processes involved. So for example, people can sweat, people can go to the washroom, and all these effects are helping clear that radiopharmaceutical that is circulating in the body. If it was only dealing with the physics, then we know everything, because we know the decay constants for all the radioisotopes that we use. But here we need to incorporate a biological half-life that will account for the rate at which the isotope is removed from the body. And again, I think we talked a little bit about this. So what we're trying to figure out is how to get this total number of particles. And when we incorporate the biological half-life, remember that we have defined an effective decay constant, which is the sum of the biological decay constant and the physical decay constant, or in terms of half-life, well, it will be the equation that we're showing down here. So what we need to do to use then is that effective decay constant, or that effective half-life. And once we know the effective half-life, then we can now go and do the integral. And that integral we typically represent it with this A with a little tilde on the top. And we call this the time integrated activity. So now we have, we're doing the integration as a function of time. This is the time integrated activity, but what that is giving us is the total number of decays that occurred in that source. So if we said that the S factor was the dose in one decay, and then I just did that integral and I obtained all the number of decays, then all the number of decays times the dose in one decay should give me the total dose. So that's kind of the idea. This time integrated activity has to do with the biologic distribution of the data. We don't know it. We don't know, each patient is different, each metabolism is different. Maybe there's a patient that the two kidneys are very healthy, but maybe there's a patient that only has one kidney. So in those two situations, we expect that clearing of the radiopharmaceutical to be different. We need to account for that. So it's hard to predict. We have to go and measure it. So that's what this time integrated activity term is giving us. But then we have this S factor. And remember, the S factor, from what I just said, it contains all the physical properties of the radionuclide. So we know those more or less very well. But in general, this equation, and this is kind of that mirrored workflow, what it's proposing is, let's combine that biological information with what we know about the physics to obtain the dose estimate. Okay, so as I'm saying, we need to measure this yellow box. So how are we going to measure it? Here's where quantitative imaging becomes so important. So let's try to determine the time integrated activity. So the way we do it is, how can we measure activity? And we've discussed this in the previous lectures, and we know that if we scan a patient, and if we do image reconstruction, and if that image reconstruction, we do it with attenuation correction and scatter correction and correcting for as many of those effects as we can, we're going to have a very accurate number of counts in that image. And if we perform a calibration in an accurate way, then we'll be able to relate counts into activity values. So again, MLEM, OSEM, all those things that we discussed before is because we need quantitative images. If we don't have quantitative images, this is not going to work. Once we have quantitative images, then we know the accurate activity distribution in the source, well, in the organs. So then you can see, for example, in the case of liver to kidney, we were interested in measuring what's the activity in the liver. We'll be able to do that very accurately from those images. But we know that this follows a curve that looks like an exponential. Well, what we have here is a to the e minus lambda effective t. So one point is not going to maybe provide us too much. So what we're going to do is let's scan that patient multiple times. So let's say we're scanning the patient 1 day after the injection, maybe 2.5 days after the injection, 4 days after the injection, and so on and so on. And what we're doing is we're collecting points in this curve at different times. Well, if we have different points there, I can now fit those points into an equation. So it can be like that mono exponential equation that we've been playing with. So when I fit those points, I'm basically what I'm doing is I'm measuring the effective half-life. If I'm measuring the effective half-life, but we know the physical half-life, then, well, we can figure out what is the biological half-life for that particular patient. So we can do the fit, and then I can calculate the area under the curve because now we know the fit. Now, that integration, in principle, the radioisotope can be inside the patient forever. If I inject, it might be there forever. So we perform the integration between 0 and infinity. And I hope you guys can go and do that integration from 0 to infinity. This one. If you do that integration from 0 to infinity, the result that you get is A naught over lambda. And I'll let you guys do that at home. But that's easy. We can determine the area under the curve. So what is the area under the curve? That's the time integrated activity. And we said, okay, that's the total number of emitted particles in that source. So okay, now we found the total number of decay particles. Let's multiply it by S. That's the part that we're missing. And we multiply by S, we get the dose. So then we go to that step 2, and well, it's important for us to know the physical properties of the radionuclide. And these are some examples of radionuclides used in therapies. Because we've been talking a lot about lutetium-177 throughout the course. So it's important for us to know that it's a beta decay, because we want betas to deliver dose into tumors. We know that the half-life is 6.7 days. We know that it has some gamma emissions that we can use to image. We know the abundance of each of those photons. We know the maximum energy of the beta particles. Well, we need all that information to come up with that S factor. So yeah, well, I mean, at the beginning you would say, okay, but look at that equation. It's really complicated. It's like, okay, how am I gonna be dealing with this? And then I have to go and look emission by emission and calculating how much is the fraction of absorbed energy in that target. Well, it's not that complicated in a way, because S factors can be pre-calculated, and we can pre-calculate those for a fixed source and target geometry. So in a way, we can just basically generate lookup tables for a particular geometry. And if you have the lookup table, then you just go and be like, okay, I can calculate the total number of decays, and then I go and look into my table, okay, the S factor for liver to kidney, and I multiply that by this, and I get an estimate of the dose. So one of the ways that we can generate those S factors is at the organ level. And this was one of the first models. So we were thinking, okay, let's approximate the average human, the average adult, with something that looks like this image that I'm showing in the right. So yeah, maybe the heart can be like a sphere. The liver can be like a trapezoid. The stomach is like an ellipsoid. And we're gonna put some dimensions there. And then we can, for this particular geometry, we will be able to know that, okay, if I put some activity in the liver, how much is the dose in the stomach? Or how much is the dose in the spleen? Or how much is the dose in the breast? I will complete some lookup tables for this model. So then we can just go and look at them and multiply by my number of decays to get the dose. Now, these models have been getting better over time. Of course, I think it's clear that human beings don't necessarily look like that. We look more like this. This is like a second iteration of improving those models. So now, again, but it's the same idea. We're going to put some activity in one of these organs. Now that geometry approximates more like how we look. And again, we can create a lookup table. We've even done this for mice. Part of what we do in research is develop radiopharmaceuticals. And the way radiopharmaceuticals ended up making it into a human is because they are first tested, for example, in mice or rats. So we also have some models for mice or rats so that we understand from the preclinical point of view what's going to happen when we inject this into a human. And we need to show some data before we can even do that. So yeah, so this is the approach that is known as organ level internal dose, because we're looking just at organs as a whole, and we're just assuming that the radioactivity is uniformly distributed in those organs. So there was a software called Olinda, because it stands for that, and that was very popular. That has been purchased by a company, so now it has to be licensed. But there's this other software that you guys can become familiar. It's free, you can download it. It's called IDAC, which is a new internal dosimetry program for diagnostic nuclear medicine. You can find it in this reference. But the way it works is basically it includes some of those S factors from one of those models. So it has the lookup tables. So what you can do is when you have your patient scans, you can go and try to determine the time integrated activity for the different organs. And then you can plot those values here. You can select the radionuclide. For example, in this case, I'm showing an example, which I selected lutetium-177. And you can choose if you want to have the estimate for the adult male or for the adult female. You input some values and you click calculate data, and you have some estimates of the dose. And then you can talk with the physicians and try to improve the therapy or make some other clinical decisions. But I wanted to have a lab in which we would use this software. We didn't have time for that, but that's why I'm showing you. Maybe you guys can go and play. It's free, and try to understand the concept. But again, keep in mind, here we're looking at an organ as a whole for an average model of the human being. There's another method of calculating those estimates, S factors, which is what we call the voxel S values. And the way this works is, instead of putting the activity in an organ, let's just create like a little matrix that is basically a homogeneous medium of tissue. Maybe most typically used water. And we're gonna put our activity at the center of that image. So you can choose how many voxels do you want to have, but it's typically a small matrix. So we're gonna put the activity there, and we're gonna see how much dose we get in every other voxel around that central voxel. This is what we call a dose kernel, or we can also say that it will be a dose filter. I don't know which are you most familiar with, which term, but we call it a dose kernel. And what we do when we have this dose kernel, this is basically telling us, okay, if I put 1 decay in the central voxel, how much is the dose that I get all around that central voxel? So when we have our image of the patient and we have the time integrated activity image, basically we have an image in which every voxel is telling us what was the total number of decays in each voxel for that treatment. Then we can take this kernel and we do what is called a convolution. So basically we're going to start moving our kernel around the image. And a convolution, I cannot get into the details of how exactly you do a convolution, but this is basically telling us it's starting to create an image here on the right that has if this is the distribution of number of decays in each voxel, and I start summing all around, then the total dose that you're gonna get in a patient is gonna look like this output. So now we're not going from organ level. Now I can have an image of the dose. This is what we call the dose map. Now I can also have a 3D image of dose. And then you can go and calculate, okay, you can go and find what is the dose in one voxel, what is the dose in this small region of the kidney, or what is the dose in this right lobe of the liver, or you can now start narrowing down to smaller and smaller regions. Yeah, so this is actually a simple method to implement. Then this is the method that is considered like the gold standard, and it has to do with Monte Carlo simulations. So Monte Carlo simulations, I'm going to explain in a moment how they work, but now we can input the CT data, the image that we get from the CT, and I can input some information about the radioactivity of the time integrated activity image. Again, the image that contains all the total number of decays in each voxel. We can combine the two and we can include that into the code. And what the code is going to do is that it's going to simulate all those different particles coming from all those different voxels traveling in those density of mediums that we measure from the CT. And it's going to do this for many, many particles, and it's going to be able to provide us a very accurate distribution of the dose. In fact, those two methods that I mentioned a moment ago, the organ level, like the lookup tables for the S values at organ level, or the voxelized S values, well, we create those tables using Monte Carlo simulations. It's just that we perform the Monte Carlo simulations for those particular geometries. So one would be the geometry of the human. If you put some activity in the liver, you perform the simulation and you can measure how much you get. Or if you want it at the voxel level, you put activity in the central voxel and then you perform a simulation to see how much dose you get all around that voxel. But Monte Carlo simulations, just a quick overview of what they are. What we need for them is, well, we first need to define our scanners if we want to do the imaging as well. We need to define how our patient looks. So basically, here's what we're telling it. Look, I have this CT and I have this time integrated activity image for this patient. So use those two. We're going to have to tell it, okay, my source is lutetium-177, and so on and so on. So we're going to start a Monte Carlo simulation, and it starts with one radioactive decay. So the simulation is just going to start generating decays one after the other, one after the other. But then it's going to use random numbers to decide what is the particle type. So again, remember that all these radioactive decays are stochastic process. So we're basically going to throw a coin to decide, okay, is it going to be the beta of this energy, or is it going to be the photon of this energy that comes now out of that particle, of that decay? We're going to see what is the position of that particle coming out. What is the material at that position where that particle is being generated? We're going to see then, we know that one particle, for example, if the simulation starts with a photon being emitted, then we know that photons can have photoelectric effect, or they can have Compton effect, or they can have pair production. So again, we're going to throw a random number, and depending on the number, it's going to statistically decide which of those interactions is the one that is going to occur for that particular particle. And while we know we have equations to calculate the mean free path for different particles, for different interactions. So it's going to keep using that. It's going to decide what's the interaction that happened. It's going to decide if it's scattered. Then if it scatters, for example, we have the Compton equation. We're going to be able to say, okay, well, we need to determine at what angle is it going to scatter. And if we know the angle of it at which it scatters, we'll be able to determine what was the energy that was deposited. Now, are there secondary particles coming up from that interaction? And okay, this code, we're going to calculate it. And we're going to do this for many, 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 many particles. And then that will give us a very, very close statistical approximation of what we'll be seeing in real life. So that's how Monte Carlo, just a quick overview. Of course, I cannot go into the details, but just think we're using random numbers to see what particles that we generated, what type of interaction we have. And when we do this for many, many particles, it approximates reality very well. And Monte Carlo, again, it can simulate the transfer of those photons and electrons throughout that surrounding media. And then it can provide us with a very accurate estimate of the 3D dose map. We got the distribution of the dose. I don't know. Dose, it looks simple. Well, I guess it's basically a simple procedure. Just go and scan your patient several times, fit the area under the curve, fit the curve to those points, calculate the area under the curve, and then go and try to find an S value. Of course, it looks simple, but there's a lot of issues. It's not that simple to implement in the clinic because it has some challenges. And let's think about some of those challenges. Well, one, we need to make sure that we are reconstructing quantitative images. Remember, it's important because we need to measure the amount of radioactivity. So if our images are not quantitative, then we're not doing it right. And as new isotopes start coming into play, we need to start improving our protocols to be able to create quantitative images of those isotopes. So that's a challenge. Well, with lutetium-177, for example, we're now doing very well. But then, for example, you have yttrium-90, and obtaining quantitative images of yttrium-90 is not very easy. Well, as I said, we need to perform multiple measurements. But when are you going to measure? I mean, can you measure maybe as soon as you inject and maybe 2 days later? Or is it better to measure every hour after you inject? I don't know. We need to figure out when is the optimal time to measure. How many times are we going to measure? Well, the more times we measure, the better it's going to be for our fit. But then you can think, well, but can I really bring the patient 10 times into the clinic to have 10 PET SPECT scans? Do we have enough resources? I mean, every time that we put the patient on the bed, there's another patient that cannot be in the bed at that same time. So how many machines, how many SPECT cameras do you have? You need technologists to scan the patients. How many technologies do we have? So it's a balance of all these resources. Image registration. Yeah, as I said, well, yeah, we collect images at different times, but if we're going to do, for example, voxelized approaches, we need to be able to know which voxel from one image corresponds to that voxel in the other image. So we need to find ways of making sure that we're doing that right. And because if two voxels don't correspond and then I go and feed the area under the curve for one voxel, then I'm getting the wrong number. Now, image segmentation, as I showed the example, okay, the liver and the kidney. If I want to measure the activity in the liver, then I have to go and draw a region around the liver just to measure the activity there. As you guys are doing in the lab number 2, you guys are working on the SUV part. We're putting a region there to measure some parameters just for that region. But I'm pretty sure if 2 of us or 3 of us go and draw the liver, we're going to have slightly different liver. So which one is the true liver? And I mean, we need to figure out the mass of the liver because remember, dose is energy per mass. So I need to understand what is the mass. If my region changes, then I'm going to have a different mass value. And what is the activity? There's all these spill-out effects of radioactivity that if I measure the mass very accurate, maybe I'm underestimating the activity. And if I measure the activity very accurate, I'm overestimating the mass. So we need to find that compromise. How accurate is the use of the dosimetry model? Can we report the values with some uncertainty? At this point, I guess people typically are reporting this is the dose, but we still don't know very well. This is the dose plus minus this %. We need to look into that. Now, some of these procedures are very time consuming and need too many resources. So we need to think on how is that we can simplify them. And yeah, Rebecca is also saying in the chat, well, not all patients have the same body habitus, exactly. And each patient is going to behave different. And that's why we need to try to personalize it. So we need to simplify these procedures. We can probably not keep thinking that we can scan the patient 5 times because that's not going to be very feasible. So we need to make it easier to see if we can bring this to the standard of care. And then there's this big challenge that despite the large number of clinical trials that have been around, considerable uncertainty still remains regarding the optimization of this therapeutic approach. So a vital question that still remains is there a dose-response relationship that could guide us in personalized treatments? So if we are able to identify the dose-response relationship, then we know, okay, if we provide this dose, this is going to be the outcome. For this particular type of therapies, this is still in research progress. We're trying to find answers for that, but we still don't fully have them. There's some data starting to come out, but we need more data. We need to show more evidence about this. And the reason I'm showing all these challenges is because I guess that's part of what we've been doing throughout this course, and this is what you guys have been learning about. And I think you guys can all help us find solutions to give cancer patients hope and new opportunities to win the battle against cancer disease. So for example, if you're a physician or if you're a technologist, you guys need to guide us, for example, in the physics side so that we know exactly where to put our efforts in. As we were talking at the beginning at some point with Rebecca, maybe sometimes as physicists, we just think that we're going to scan uniform spherical patients in vacuum and that we can do this every 10 seconds and get a super nice image, which of course is completely out of reality. We need to know these patients are sick. It's not very easy for them to come to the hospital every 2 days to get a scan. If you are, for example, a software developer, you can help us build software that makes all this process of segmentation, registration, annotation, grouping all the data that is needed, doing the calculations. We can make those things simpler, maybe using software. As physicists, we understand all these procedures. We're going to keep working. We need to keep working on optimizing the images, getting better quantitative images, improving the resolution as much as we can, improving the noise, because all that is going to help us, of course, in these procedures. If you are engineers, well, we need, again, it's all the hardware. We build better machines. What type of detectors are there? How can we make all these computers and all these reconstructions faster? The chemists and the biologists, we need to still look for new targets. With the chemist side, then we need to try to make more molecules to target those targets. And yeah, I don't know. So I think that's everything I had. And I want to say thank you. As I said, this was our last lecture. I hope you guys appreciate it. It was great having you guys in this course. Armand and I talked at the beginning of the term, and we definitely made this our top priority this term. Yeah, we're here whenever you guys need to reach out. Good luck in your new endeavors and your careers. And yeah, thank you very much. It was great having you all.